Good afternoon to all. I hope you had a great day. I mean, I personally enjoyed. A lot of great people in the profession, so, fantastic subject. Thanks to CTBUH for creating such great atmosphere here. I hope I don't bore you too much, but looking at the engineering point of view for designing tall building in a historic city like London, my intention is just to go through some of the challenges that we typically face designing tall building in London, and we've done a few of it all over. So I will try to take you through some examples of what we need to do and what we have to do. To start with, any tall building in a historic city like London requires a great ground entrance to the building and the streetscape. To have a ground place that welcome people to the building, encourage the building to come to the building, make it an interesting part of the area. It's important that you create permeability. And unfortunately, on tall building, this defies the nature of gravity. I mean, when you come down is where you need all the area and where you need to put all the material for lateral stability and just for the sheer vertical force. So, but as engineer, our responsibility is just to make sure that working with the architect and the design team, create that space that is amazing and is special. And for those of you who have gone to London Bridge Tower, Shard of Glass is one of our buildings, basically to do that, columns at the base that they are about 20 meters long had to be no more than about 500 wide and about 800 mil long, in a direction that reduces the obstruction of the view and to open up the space. So if you go there, you'll see that it's an amazing structure at the base. Similarly, if you go, for instance, to the new, well, this is not built yet, but when Ian Simpson designed the Blackfriar, I think later on he does have some talk on the building. First of all, the sculpture of the building is quite different from a normal building, but the sculpture at the base just thinning down, creating more space at the base was an inherent part of the design. And it was for a tall building, because you're dealing with large forces and large lateral force, is not the area to open up the space or to make it smaller than the top of the building, but just to create this movement and to create economical and viable solution to generate this area. I mean, we have to work very closely with the architect to come up with the solutions that is viable for any particular project. Similarly, on the Pan Peninsula is another one of our projects. The base of the building, because you are in between the two buildings, it does create some kind of environment that wind become an issue. Now, John Kilpatrick will go through all so I'm not going to get too much in detail about the wind engineering and the mitigation of wind at the ground level, but basically we had to come up with massive massive canopies that also is inherent part of the architecture to achieve this. Similarly, you are right next to an existing old dock, so you got to make sure that the structure of that it works with the environment, with the dock, and it becomes part of the environment. Then you go to other areas where you do have, like in Principal Place, that's in Bishopsgate Goodyard, right next to Worship Street Bridge, where we had, I mean, if you look at the right-hand side, that was the TfL cuttings running through the space, and the idea was to build right next to it. So the picture on the left showed that how we worked, after working with Foster on many different scheme of supporting the deck over that area, we come up with the solution that was viable and ultimately could provide the architect and a space, a beautiful space that welcome people and get the people into the building, and at the same time to avoid any kind of vibration and noise generated from the railways into the buildings. This is actually a one Arab project, but again, I thought I'll show you that we are somehow involved with it as a client engineer, but Arab did all the engineering on the project, and it just shows the magnificent space that can be created by a collaboration between the engineer and architect. These are, at the bottom of the building is about 28-meter long columns. Now again, these are the area that you have the maximum force on the bracing, on the lateral bracing and the gravity member of the structure, and is not the place to make it 30-meter on brace, but because it creates something special and because it will bring people into the building and make a great place, this area that is worth looking into, but come up with the best possible solution for a particular project. Then you come to an area like the Canary Wharf that, if you take a look at the picture, that's in 1982. I came to London in 1988, and again, it has its own, it has its own requirement, it has its own issues, but it's a little bit different from building in the city. You are going to an area that is economically a little bit depressed. So when you start designing buildings in that area, the first building, the most important part of the building is to make it economical, to make it very efficient, very economical, so it could become viable for the next generation, which is the city, which is the buildings that we are building right now in the area. So in that case, you basically changed a place that nobody used to go to, a destination place, by working with the architect and with the client to create something very special for the City of London. These are just different areas and different part of the Canary Wharf that we have to deal with the different type of issue, including the old undifused bump in the area when we were doing the excavation. Then the next issue with the tall building is the dealing with the spider web of infrastructure. I mean, you are dealing with an ancient city. There are a lot of sub-infrastructure in there already that you have to deal with. So again, on the principal place, we do have a lot of excavation down there. So archaeological information is very important. You got to make sure that the archaeology is intact, and your duration of the construction and method of construction allows for the archaeological activity to take place without disturbing the time frame of the building construction. In addition to that, you are dealing with utility infrastructure that's already exists there. And so again, by working with the design team, you come up with the best possible solution. Should I go with a hand dug caisson in the middle of the utility? Should I cantilever the building over the utility, or spend 4, 5, 6 million diverting fiber optic from the site? So all of these are quite important in a city, historic city like London. Ludgate's and Samsung House with PLP, another area now. This just shows you, I'm not going to go through every one of the items, but it shows that how many different things a structural engineer has to deal with just in one site, and together with the architect device, the best system that makes the project not only economically viable, but is a great architecture and a great piece of London, peaceful future of London. Different type of one, 261 City Road, we're dealing with different type of thing. Again, the LUN Northern Line runs to one side, and the UKPN tunnels are underneath them. Shell Center, we just got planning, fantastic site, great number of building. Basically, the whole building is underlain by tunnels. Bakerloo line is running under the building. Northern line running under the building. Jubilee line is right next to the building. So you have to build the building on top of this maze of LUL tunnel. At the same time, you need to make sure that not only during the excavation, you don't disturb any of this tunnel, but after you put the building on, you don't disturb the tunnel by additional load. So the movement of this tunnel during the construction, during the design and construction, and furthermore, right at the end of the project, you have to have a project that avoid vibration, that mitigate vibration coming from the tunnel into the building. So this is, again, another picture of another job in Canary Wharf. Basically, you have to deal with a grade 1 listed banana wall, for instance. I faced this since I started that. Banana wall is a very important thing. It's a grade 1 listed building. You have to avoid it. You can't touch it. So again, working with the architect and working with the design team, coming up with different way of avoiding it. I mean, in here, we just created a sloped column which takes the load into the building. On another job, we just use the A-frame on top of it, and we in some area, we try to expose it. The shard of glass, again, surrounded by Northern Line, Jubilee Line, National Rail, every possible infrastructure that is in the way. And in addition to that, we had a water main on the St. Thomas Street that leaked during construction of some of the buildings. So we were very worried about causing disturbance to that, and we had to make sure that movement of the ground is absolutely minimized to millimeters. In addition to that, you have to deal with the existing piles that was there for the old Sadek Tower, and to go through it and come up with a top-down construction, not only on this one, but the one next door, the place, to make sure that the building can go up while they are digging underneath and while they are exploring. That was on the place, exploring the archaeological issue. Again, in a project like the Shard, you don't want to come to a very congested area and start putting steel together. So for that project, modularization was very important. We had to make sure the top of the building is fully modularized, and the whole top of the building spire was constructed at the plants, and then deconstructed, brought to the site, and then constructed at the site with no issue. On the place, we had, again, a maze of tunnels and network rail asset underneath the building in such a way that we couldn't found more than 50% of the building on the ground. So the area of the footprint of the building at the base is probably 50% of the 50% of the building above. And for that reason, we came up with which we basically hung the southern face of the building and eastern face of the building by the cores. I mean, it's very unique solution for this project, because if we went back and added, like for instance, 2-story trusses at the base of the building, we would have taken so much area of the building that it would have made it uneconomical for the net to grow. So basically, the whole building in two sides is hung off the core, and the core was preset to allow the building to go up during construction without any issue with the cladding and with the architectural fabric of the building during and after the construction. And basically, this is what area that you need to avoid. You deal with a city that you deal with life of the people. You deal with the population that going through many of these stations, like London Bridge Station is I think the second largest station, I mean, as far as population in London. So you need to make sure that accident like this does not happen during the construction. Another item that is very important on doing tall building, again, I'm not going to get too much into it because different people are talking about it, is the use of building information management to make sure that because of the integrity of the foundation and because of the complication of the infrastructure on the building, you make sure that everything is fully coordinated. And when you find items that in the ground that you wouldn't expect to have or didn't show up during the survey, you could very quickly get into it, modify it, and we did that very successfully in the place, and is built in record time and is up. Okay, that I will leave John Kilpatrick to get into the wind aspect of the talk.
Well, thanks, Kamran. I'm going to talk about the wind aspects of tall building design, but I'll just start off by saying there's been many other CTBUH conferences where RWDI or wind engineering consultants like us have talked about the ways we can make structure help the structural engineers make their designs more efficient, reduce the embodied energy, etc. I think today I plan on focusing more on tall buildings and the effect on urban habitat. So wind, and I thought I'd put it in a sustainability context. Sustainability implies structures that last, have minimum environmental impact. Wind and other climate issues can cause damage. You know, there's damage to structure, damage to the environment around major developments. There can be unpleasant wind conditions caused either for pedestrians or perhaps for in air quality around developments. And of course, sustainability also implies we're thinking ahead, we're thinking about the future. We often get asked about climate change, and we often dodge the question, and so you might want to ask about that later. Types of risks from wind, well, things like structural failure, aeroelastic instability, cladding failure due to wind load or debris impact in hurricane or typhoon regions. There are actually, wind can transport snow and cause failure of roofs due to deposition of snow. There can be serviceability problems. That could be human comfort in high-rise buildings. It could be pedestrian winds at the base of structures. And of course, there are air quality issues and a number of others, which I'll talk about. Wind flow around buildings, it's quite complicated, and it depends on whether it's a bit different if you have a tall building or a squat building. The effects of wind and the flow around a building can be quite different based on the wind direction. And the proximity of neighboring buildings can also affect the way wind behaves. Safety and comfort is key, particularly in the UK. When we submit planning applications, an environmental impact assessment always includes a wind impact assessment. We do this using a couple of tools. Key one for us is the wind tunnel, but we also use computational fluid dynamics to assess winds around developments. What is the impact of height exactly? Well, very crude example using CFD. On the top row, we have a simulation of buildings which are of similar heights. On the bottom row, the central building in the array has been raised by about 30 meters, and what you see on the bottom two right-hand panels is more red at ground level. That's indicative of higher winds at ground level. So standing proud of your environment does tend to cause problems at ground level. How do we assess whether we have a problem or not? Well, there's various comfort criteria that can be used. In the UK, we use the Lawson comfort criteria, but all criteria basically look at wind speed and the percentage of time that certain wind speeds are exceeded to make an assessment of comfort. The assumption behind all of these criteria is typically that people are dressed appropriately. So if we're in a cold climate, if it's uncomfortable because of temperature, people tend to put a jacket on. If it's a little bit hot, they tend to take their sweater off. But we don't always have that luxury, and I'll come to that in a second. I thought I'd throw a case study up here, something we did in the not too distant past, which involved the Shard. So on the bottom right of the slide, you see Guy's Hospital. There are various locations at ground level. The ones indicated in yellow are windier than the rest, and there's one or two of them. There's a yellow symbol circled in red, which indicates that could actually be a safety problem. So users of the site, people that worked around the hospital, were aware of these conditions. The interesting thing about the Shard, actually through the use of various mitigations, which include some of the very large canopies near the base of the structure, the wind environment at ground level has improved over the previous wind environment. So there's a case where something's standing proud of its environment. We know there could be some issues, but using some intelligent design solutions, you can mitigate those. So I talked about wind comfort, and maybe in a climate like the UK, we can adjust our clothing to compensate. In other climates, perhaps in southern Europe, but certainly as you get further towards the Middle East, temperature is a factor, humidity is a factor, the exposure to the sun's a factor. The plot on the bottom right, we're seeing various effects of full sun or complete shade. The vertical scale is the sort of the perceived warmth. So we can see that wind are the various curves. The more wind there is, the less warm a condition is perceived, and the less sun there is, the less warm an environment is considered. You know, that can have implications on tall buildings that cast long shadows in certain environments. There are criteria that are used to assess thermal comfort. This is one SPM-V star. It's the development of an ASHRAE criteria. They do recommend, they have different thresholds of acceptability. We can use those blindly if we wish, but we've gone to the trouble of taking our own comfort surveys in warm climates like Abu Dhabi to try and qualify those criteria and improve our understanding of them. All of the following are useful, particularly if we're undertaking or working with teams undertaking master planning exercises. The arrangement of buildings, on the top two plots, the arrangements of buildings can be modified to introduce flow into various areas. As we saw from the previous slides, more wind usually means less warm conditions, less perceived warmth. So in a hot climate, more wind would be beneficial. And we can help to rearrange the layout of cities. If we have the luxury of being able to do this at an early stage, you know, the layout of streets can be arranged to take advantage of shading to provide some cooler conditions as well. Other impacts of wind, well, wind is important, particularly when we're looking at things like the pressures on a facade for HVAC design. Natural ventilation is a very, well, it's always been a hot topic. I would say we see more and more developments that are taking advantage of natural ventilation. The wind tunnel is a great tool to establish the boundary conditions that you might use in any computational or analytical assessments. Of course, the shard, if we stick to the shard as an example, the dispersion of pollutants and odors is important. So how the exhausts from the shard might affect the local hospital, Guy's Hospital, is important. Likewise, how the hospital exhausts might affect people in the shard is important. So again, it's all about urban habitat, and what we're trying to help people with is ensure that there is a high quality environment for end users of the development. With a lot of tall buildings, the shard is one example, but there are many. Acoustic noise can be a problem. So architectural features, vortex shedding from those features can have certain resonant frequencies, some of which may be audible. There may be oscillation, vibration due to cavity resonance that might create a tone. There could be edge tones. This is a case study of a sunshade we actually, a client reported a problem with. And we did take some full-scale measurements, and were able to measure various tones at high frequency, which we were not able to match exactly in the wind tunnel, but we were able to create a tone in the wind tunnel that wasn't too far off the full-scale measurements. What that enabled us to do was work on some solutions in the wind tunnel to mitigate that noise problem. Snow drifting is a problem, maybe not in the south of Europe or in the Middle East, but certainly in northern Europe it's a problem. There's various ways we can look at snow drifting. Building codes, we can use water flume or wind tunnels, and computational assessments. This is an example of an assessment made in a water flume. So a model scale test, bottom slide, demonstrating the type of accumulations you might get because of blowing snow, and that same building with the full-scale snow drifting. So qualitatively, there's quite good agreement between the two. Driving rain is important. Where does it go? You know, we know we can work out how much rain falls in various intensity of wind events. We can work out the angle of driving rain. You might say, well, what is the problem? Driving rain just runs down the facade and we collect it all and it ends up in a gutter somewhere, which is true for the most part, but more and more facades are sloped, they're curved, they have perhaps waste lines in the case of the one Blackfriars project that Kamran showed. So where does the rain go that's being driven by the wind? It's looking at some of these climate issues, climate-related issues, wind being one of them, in more detail, helps improve the design of the structures and the habitat we live in. So, final slide is just to say this. It's a quote from Renzo Piano: "The city is fragile and vulnerable, so we have to be careful." And I think that's where structural designers, architects, and ourselves as wind engineers can contribute. Thanks very much.